So we define with you indefinite Lebesgue integral as the following function. If function f small is integrable, then function f capital is well defined. It's easy to see, and what is more, it is continuous, and also it has bounded variation, and we proved with you two lemmas. Lemma 4 is here, and lemma 5, I want to say it. We have that if integral from a to c f equals 0 for any c, then we have that function is 0 almost everywhere. So please your questions about the proof of the last lemma. No questions. Okay, now now we will see that since function is this Lebesgue indefinite, since this indefinite Lebesgue integral has bounded variation, so it's integrable, and the aim of two theorems that we will, two results that we will consider with you now, is to show that derivative of this indefinite integral, it is just function f small, f small. So it is positive answer about the question on the question of invertibility of Lebesgue integral. The first result will be again lemma. Let's consider this is a lemma. Lemma 6. Lemma 6. Lemma 6. It's preliminary version of the main result. Suppose that function is bounded. F small is bounded. We have that function is integrable on the interval a, b, and function is bounded by some constant m. Then we have that the derivative of the integral from a to x f dt, it is just f of x. It is f of x. So this is the, it's not quite good. Maybe let's write almost everywhere. So derivative of this function, it is f small almost everywhere. Okay, proof of this lemma. Once more, f it is just the integral from a to x. F small has bounded variation. Has bounded variation. Therefore, by the theorem 3, by corollary of theorem 3, almost everywhere there exists finite derivative. There exists f prime. Almost everywhere there exists f prime of x. Now, what is f prime? Of course, it is the limit of corresponding sequence. We will take with you the sequence fn of x, as we did before when we discussed the derivatives. F of x plus 1 over n minus f of x. The first natural sequence that has limit. Yeah. Then what do we have? By the way, this is by definition. We will take it. Yeah. But again, if you write this in terms of this integral, then what is this? It is n, and here integral from x to x plus 1 over n f dt. Clearly, yeah. If we will substitute in this formula the value of f capital in terms of function f small, clearly, yeah? Now, then what do we have for this sequence? Then we have two facts. The first fact is that fn converges to f prime almost everywhere. Since it's derivative, yeah? What is the derivative? Derivative is the limit of sequence of that type. And since derivative exists, then this almost everywhere. Almost everywhere we have this convergence. And the second fact is that since function is bounded above by the same constant, by some constant m, we can estimate it from above, put m in front of the length of the interval 1 over n, and we will have the value of the function fn is less or equal than m. So we are in we have all conditions of so-called bounded convergence theorem, yeah? Or if you want, we can apply here Lebesgue-dominated convergence theorem. Since now this M is dominating function, it is integrable on the interval AB, consider it as finite interval, etc. Yeah? So by Lebesgue-dominated convergence theorem, or by the theorem about bounded convergence, bounded functions on bounded interval, we have that integral of Fn, any kind of integral from a to any value. Let's put here value c. Fn convergence to integral f prime from a to c. Okay? So, please your questions about this one. And this is, of course, for any c in the interval AB. Huh? Is it okay? Now, once more. This is, for example, Lebesgue-dominated convergence theorem. I mean this implication. Now, let's look more carefully. What is the integral? What is the integral from a to c Fn? Just by substitution, yeah? So this is, we will have n, and here integral from a to c of f of x plus 1 over n, and subtract dt, dx indeed, yeah? And minus integral from a to c f of x dx, yeah? Just substitute. And then make here, we can do here natural shift of variables in order to cancel main part of these integrals, yeah? It's clear, yeah? Because what is the first integral? The first integral is integral if you take this as a new variable, the differential will be the same. So now it is a plus 1 over n, and here c plus 1 over n f dx. The first integral is absolutely the same as that one. We did this with you before. So we will cancel all this stuff, and we will have here n, and here integral from c to c plus 1 over n f capital dx, minus integral from a to a plus 1 over n f capital dx. Okay? Please your questions about this form clearly, yeah? We will cancel common integral over the common interval. Now, and now we will see what we will have if n as n goes to infinity. As n goes to infinity, then we can find now the limit as n goes to infinity. Since function f is continuous, the same as for Riemann integral. If this function is continuous, then of course it will take value, just the value of this function at point c, yeah? Multiplied by 1 over n. Is it clear or not? Yeah? So, look, yeah? Since if n is very large, it is the value of the function at point c plus very small value, which is neglectable if n goes to infinity, multiplied by 1 over n. Clearly, by continuity. By continuity, we have here f of c minus f of a by continuity. Continuity of function f capital. We proved with you in the lemma number 4 that function is continuous. Continuous. Now, but what is this? That is, what is this difference? It is just the integral. If you take what is f of a. F of a, of course, is 0, yeah? So it is integral from a to c. We have that integral from this one, from a to c, fn. It has the limit f of c. F of c, since this is 0, and f of c, it is integral from, by definition, integral from a to c f dx. F dx, okay? Or dt, it's better to write maybe. F dt. Please your questions. So, we have that this sequence has a limit. By Lebesgue-dominated convergence theorem, this on one hand, this is limit. This limit, it is integral of the derivative f capital prime. On the other hand, by these simple arguments, this limit, it is the value function f capital at point c, that is this integral, yeah? And this from here, from here we have that integral from a to c f dt, it is the same as integral from a to c f capital prime dt. And this is for any c. Now we can apply lemma 5. Lemma 5. Lemma 5 now eventually will give the result. Lemma 5 says that f capital prime, it is f small almost everywhere. Please your questions. This is just what we want to prove. Okay? I want to repeat the main idea, the main steps of the proof. We consider special sequence. This sequence now is bounded, nice condition, bounded by the same value m capital, since the same as a bound of function f small. On the other hand, it's convergent almost everywhere to derivative which exists by lemma 4 and the corollary of theorem 3. Therefore, Lebesgue convergence theorem gives that this sequence has a limit, and the limit value it is just this integral. But on the other hand, this limit it is that one, and this is for any c. Therefore, f capital prime it is f small. No questions. Huh? Now, this is positive answer to the question 1 about invertibility of Lebesgue integral. Therefore, Lebesgue integral inverts at least bounded functions, bounded derivatives. Okay, if it is derivative of function of capital, then we will have that it inverts it. But in principle, let's see that we have this. We can generalize as usual if you want to prove some fact. Rather often, in the theory of measure integral, we prove this fact firstly for some class, for example, for finite measures, and then generalize, extend it for sigma finite or for bounded functions, and then for any functions. So the next result it is theorem 7, and this theorem 7 will be just a result of that form, but without restriction. Without restriction, that function is bounded. For any function, for any integrable function, we have that f capital prime, it is f small almost everywhere. So again, I'd like to recall you that fx, it is the integral from a to x f dt. Okay, so it is an extension of this theorem, of this lemma, to the general case of any integrable function. Let's prove this. At first, let us suppose that function is non-negative. Let at first function be non-negative. If we will do this, then for general it will be easy to do, since it will be sum of two non-negative functions, any function f small. Now, function is non-negative, then we have that we will reduce the situation of lemma 6. We will take function fn. Fn, as usual, it is the cut function. It will be fx if we have that fx non-negative.
The difference is it is being bounded. The difference between lemma 6 and 7.
What difference you mean?
I mean, isn't it the same, this lemma and 7? Only the f is bounded case.
Yes. So lemma is particular case. This is particular case where function is bounded. Now we want to extend this result to generalize it for any function. So without loss of general, of course, we can say that function is unbounded now. Yes, it's otherwise we will have immediately lemma 6. So function is unbounded. But function is bounded. Nevertheless, we can approximate it by bounded functions. So this is the idea. And then use some passage to delimit. So if fx are less or equal than n, and n otherwise. So now we have some sequence of bounded functions here. Then what do we have? We have that this sequence fn increasing to function f, of course. Yeah, clearly, as n increases. Then we will take, let us consider the function function integral of the difference. So for function gn of x, what is gn of x? It is integral from a to x f minus fn dt. We have the function f is larger, not smaller than f of n. So this is some positive, non-negative function. We integrate some non-negative function. Okay? And we have that this function gnx increases with respect to x. Okay? So, of course, because it is integral from a to x is of positive function. This function is positive for fixed n. For fixed n, we have some function which is integral of non-negative function. Of course, this integral is larger. Yeah. Now, for this increasing function, there exists a derivative. Thus, there exists gn prime almost everywhere. Thus, almost everywhere there exists derivative gn prime, and not only exists, but it's non-negative. Non-negative since this function is increasing. Almost everywhere there exists non-negative derivative. Okay. Here, what do we have about function f capital? F capital, our function f capital, it is the function gn of x, yeah, and plus, just we need to take this sum, yeah, plus integral fn dt from a to x, clearly, yeah, just by derivative of the integral, we have this. Therefore, from this representation, we have that function f capital is differentiable almost everywhere. This function is differentiable, and this function is differentiable. And what is more, we understand what is the derivative of this function, since now function is bounded. Yeah? By lemma 6, we have that derivative of from a to x fn, it is almost everywhere fn. Yeah? This is lemma 6, and this for fixed concrete n. This is bounded function. Okay, this is lemma 6. And therefore we have that almost everywhere there exists derivative f prime. And this derivative f prime, it is gn prime plus fn. So please your questions about this line. We take function, sequence of functions, but now n is fixed. We fix n, yeah? For fixed n, we have this cut function. Then we consider gn as the integral of this difference. Since this function is non-negative, the function increases with respect to x. Therefore, by theorem 1, it's differentiable almost everywhere. Derivative, of course, is non-negative. Now, function f has this representation. The second term is differentiable by lemma 6. And we understand what is the derivative. Therefore, we have this form. Okay. And this is almost everywhere there exists. And this almost everywhere is more or equal than f of n. More or equal than f of n. And then from here, we can move n to infinity. Tend n to infinity. And then what we will have? There is no n on the right side. We have that f prime almost everywhere is larger than f, since this is convergent to f, yeah, increasingly. Now, and that's not all. We will integrate, and we have that integral from a to c f prime more or equal than integral from a to c f. Okay? This is the first part. We want to prove that they are the same almost everywhere. We will reduce this again to the situation when these integrals are the same for any c. For any c, yeah? These integrals are the same. And this is the first half. We have more or equal for any c, integral of f prime more or equal than integral of f small. Questions about the first part? Since second part now, is just the corollary of the theorem 1. On the other hand, we want to prove inverse, yeah? How to prove this inverse? We have that this function is positive and derivative exists. We have existence of the derivative, yeah? Derivative exists, and since function in this first case is positive, we have since f we have non-negative, we have that f prime is more or equal than 0. Yeah? F prime more or equal than 0. No, it's not quite good. It's better to write that f is increases. It's the same here. F is increases. So function f, it is integral of positive function, so it increases with respect to x. And we can apply the theorem 1. By theorem 1, we can see there, we can f capital instead of f small. We have that integral from a to c of f capital prime less or equal than f at point c minus f at point a. So this is the core. This is the fact of theorem 1. Theorem 1. Any increasing function is differentiable and derivative is smaller than not Newton-Leibniz but inequality of Newton-Leibniz type. Okay? First theorem. You can see this now. What is this integral? This integral, of course, the second is 0. The second is 0. The first is integral from a to c f dt. So now we have eventually that this integral, we have that integral from a to c f prime equal integral to a to c f. On one hand, this is more or equal. On the other hand, from here, it is less or equal for any c. For any c. From here, by lemma 5, we have that f prime is f small almost everywhere. So, if important result, please keep it in mind. It has some applications. We will use it. For example, we will consider with you, if we will have time, Sticklow functions and some other applications there are. So, if function is integrable f small, the corresponding indefinite integral, Lebesgue integral, is differentiable. And derivative of indefinite integral, it is just function f small. Please your questions. If you do not object, I will not write here lemma 6, but immediately I will write here the theorem 7. Theorem 7 so says that if function is integrable, then we have that integral from a to x f derivative almost everywhere f small. So please your questions about this theorem. Huh? No questions. Okay. It was paragraph 4.6.4. Now let us look at absolutely continuous functions. There are many kinds of continuity. There are continuous functions, uniformly continuous, approximately continuous. And this is rather strong type of continuity, absolutely continuous functions. This is 6.5. The most important class maybe of absolutely continuous functions, it is just indefinite Lebesgue integral. So please write absolutely continuous functions. Definition. I don't remember. Indeed, we considered something like this with you in first lectures, but maybe I did not give you definition, even if I did. Let's repeat it again. We say that, let's start from f capital. F capital is absolutely continuous. If you do not object, I will use immediately this notation. It means it's absolutely continuous on the interval AB. Yeah. If by definition, for any epsilon there exists delta such that for any collection of intervals, for any intervals I, n, bn, disjoint intervals, of course, inside of the interval AB, width, the sum of lengths of intervals bn minus an is smaller than delta, it follows that the sum of f of bn minus, indeed, let's take an, is increment is smaller than epsilon. The summation for n. So this is the definition. This is definition. So in principle, this definition is better. What kind of sequences we can consider? Indeed it's not so important, but let's in the definition define as a finite. Okay. So we suppose that they are finite sets, finite collections, but if it's for finite, then it can be extended somehow for the infinite case as well. Now, this is definition of absolutely continuous function, and trivially, what do we have? Clearly that if function is absolutely continuous on some interval, then of course it is continuous, and what is uniformly continuous, trivially, yeah? Since uniform continuity, it means only the distance smaller than delta for any pair, then it's absolutely clearly that f is uniformly continuous, and of course it follows from here that it's continuous at any point. So this is some rather strong condition. Now, in order to understand what is this U class of functions, we will consider with you some examples. And then we'll draw some diagram. Maybe I will draw immediately this diagram. So what do we have? We have some collection of continuous functions, yes, on the interval AB. Here, not important, closed, open interval, just continuous. Now, and there are some functions with bounded variation, Of course, it has bounded variation, not necessarily it's continuous and the reverse, as we understand with you. We will see with you that absolutely continuous, it is something which is just not intersection, but inside of this intersection, okay? It's not enough if function is continuous, and if it has bounded variation, that I'm not sure that it will be absolutely continuous. There is some Banach-Zaretsky theorem. We will consider this a little bit later, yeah? But at least we see with you that any absolutely continuous function is continuous, and as we will prove with you in 5 minutes, in 10 minutes, that any absolutely continuous function has bounded variation. So it is something in the intersection. And now let's consider examples. The first example, it will be just the function, the best one, continuous, absolutely continuous bounded variation. Take any indefinite integral. Take integral from a to x, f dt, for any function which is integrable on the interval ab. And if you will take this function f, then we prove with you that it's continuity, but if you will look at the proof, indeed, this integral is absolutely continuous. So
if something is bounded variation, we say its derivative.
Yeah.
It's almost always
Yeah.
Not to be continuous, the function.
Of course, if it's bounded variation, take characteristic function. This characteristic function is very good. It has bounded variation. Its derivative has almost everywhere, but not continuous. Okay? So I want to give you some illustrations of that one. First of all, if you take integrable function, then this function will have bounded variation. We proved with you, and we proved with you that it's continuous, but indeed it is absolutely continuous. Lebesgue integral has absolute continuity property. Yeah, we remember this. So again, this integral is something better than usual absolute continuity. Since usual absolute continuity of this function f, it means that the sum of integrals an bn, sum from 1 to n, of f dt is smaller than epsilon. Indeed, we want to prove this one, yeah? We want to prove this one, okay? But we have something stronger, yeah? So this is some particular case. We have that integral of a modulus f is smaller than epsilon for any a such that measure of a is smaller than delta. So a here of any nature, not necessary union of intervals, okay? If it works for any a, then of course it's valid for special a, which is the disjoint union of intervals. So we have that this is absolutely continuous clearly, okay? Now, about your equation, now let's take, okay, maybe let's take this as a trivial example of function which is bounded variation but not continuous. So take characteristic function of any interval AB, yeah, 0, 1. So this characteristic function is bounded variation, yeah, but is not continuous, of course. Is not continuous, clearly not absolutely continuous. Now, this third one. The third one, let's take counter function. It's an interesting example. So, counter function, f, it is counter that we considered in the beginning of the lecture today. I mean the usual counter set, counter staircase. What do we see? What can we say about this function? Of course it is continuous, yes? Of course it is continuous. Of course it has bounded variation because it is monotone. It's monotone and bounded, so clearly total variation is 1. You see? It's continuous, it has bounded variation, but it is not absolutely continuous. So we will see with you that in order to be absolute continuous, this is not enough. It must have some additional so-called Lusin property. This is later, yeah? So we have that f, but this function, so it is here, yeah? It has bounded variation, it is continuous, but f is not absolutely continuous. F is not absolutely continuous. It can be proved in different way. Particularly, we will show with you that if we will prove with you, if we will have time, that if function is absolutely continuous and if derivative is 0 almost everywhere, then we have that f is constant, yeah? So it will just contradict to the condition, yeah? To the result that we will prove with you. So derivative is 0 almost everywhere. But then it's more easy to see the lack of, the shortage of this function, the lack of absolute continuity directly, yeah? Because what do we have? We have that function is not absolutely continuous. How to show this directly? There exists epsilon, yeah? There exists epsilon. Take epsilon equal 1 over 2, for example. Such that for any delta, there exists sequence of intervals. There exists sequence of intervals an, bn from 1 to n, such that disjoint. Such that we have the length of intervals bn minus an is smaller than delta, but nevertheless, we have that the value of the function, difference value of the function is smaller than 1 over 2. Of course, we can do this easily because we can cover, given epsilon, we can cover epsilon, we can cover counter set, it has 0 measure. We can cover counter set by finitely many intervals for any delta, finitely many intervals with common length smaller than delta. Since measure is 0, measure of counter set is 0, it's easy to do, yes? But then what we will have? Why it will be more than 1 over 2? Since on the complement to counter set, counter function has no increment. All increment is just on counter set, okay? All growth of function f inside of counter set. So we have 0, we have 1, and now we cover this counter set, yeah, by these small intervals, you see? Then what do we have? We have that length of these intervals is smaller than delta, but increment is larger than epsilon. Why? Since the total increment of the function, since the increment total increment of the function is 1, total increment of the function is 1. But increment of the function on this complementary intervals is 0, because this point and this point, they are on the same interval from the complement, okay? The function is constant. Therefore, we have, once more, all growth of the function is inside of counter set where we cover this, okay? So it will be not only 1 over 2, it can be taken as close to 1 as we want, okay? Please your questions. Function is not absolutely continuous. And this is the first, the simplest example of absolutely continuous function which is not absolutely continuous. Okay? Okay. So
don't use the term, for example, continuous almost everywhere.
What?
Continuous almost everywhere, for example.
It's not quite good. Yeah, of course, there is concept function is continuous almost everywhere, or function is equal to almost everywhere equal to continuous function. But in this definition, we just consider very concrete function. It is continuous, but not almost, not absolutely continuous. Okay. Since we must be careful if you want to define this concept of absolute continuous is considered in the interval. Okay. In principle, we can do something like this for any measurable set, then it will be, I'm not sure that it will be very useful. Okay. So just for interval, we consider this. So it should be everywhere or not. Now, so please your questions about this example. Now please look at the example. So indeed it's enough, yeah? So of course it's easy to find continuous function. Okay, what is the example here? Example here, function is continuous, but not bounded variation. We considered with you this oscillating sign, yeah? So what is example number 4? Example number 4, f equals x multiplied by sine 1 over x, yeah? Sine 1 over x if x is positive and f of 0 is 0. Look, this is continuous function, yeah? We understand with you continuity. And this, we discussed with you, I hope you understand that function. By the way, I'm going to give you something like this in the homework, or maybe in the midterm, to analyze some family of functions with respect to parameter. So typical examples are x alpha and here sine 1 over x beta, or maybe with 2 parameters to check when it is continuous, absolutely continuous, bounded variation, integrable in one sense, integrable in another sense, or maybe you can look, the book, good problems are in the book of Bogachev with logarithm, etc. Take x logarithm of alpha x, etc. There are many interesting families. Now, but at least for this function, we understand it does not have bounded variation. Variation is infinity, yeah? Because we understand how to show this directly. That is, we take concrete sequence of points, and the variation will be kind of sum of the harmonic series which diverges, okay? Now, and since, as we will see with you now, the absolute continuous functions are inside of this family, so it will be also outside of the class of absolute continuous function. But the lack of absolute continuity also it's useful to check directly. How to do this? Also not very difficult, because by divergence of this harmonic series, yeah? So what does it mean, lack of absolute continuity? Again, epsilon 1 over 2 for any delta. And then for any delta, we will take just interval with small lengths, yeah, this small length, and inside of this small interval, we will take the an bn of that type, okay? And then we will have that sum of this finitely many. Then some of them will be smaller than delta, yes? But sum of increments of the function will be some part of harmonic series, which will be larger, larger, and larger, and eventually it will be larger than 1 over 2. So this is directly to see that function is not of bounded, is not absolutely continuous, okay? Of course, it's very, very easy to take some hyperbola, which is not continuous, which is not bounded variation, etc., etc. Okay, if no questions, then the simple remark, by the way, simple remark, but maybe useful, that if from here we will see with you that Lebesgue integral inverts any bounded derivative. Look, simple remark. If we have that function f capital is differentiable, not almost everywhere, and derivative is bounded, uniformly bounded, okay? Then we have trivially by mean value theorem that function is absolutely continuous by mean value theorem. Clearly, yeah? Because what is this by mean value theorem? If function is differentiable. Oops, why did not you correct me? It is, of course, f capital. If I started from f capital here, then please write f capital here as also. Okay. Now, since mainly we will apply this concept to f capital, to indefinite integral, to f small is integrand function, f capital is integral. Now look, of course, it is just integral of f prime at psi n multiplied by bn minus an. So clearly, we will have trivially this inequality, yeah? By mean value theorem, it's here. So simple remark that functions with bounded derivative, if function has bounded derivative, then it is absolutely continuous, but not inverse. Not inverse. It's not difficult to construct differentiable functions such that derivative is unbounded. Take something as sine which oscillates, derivative is large, but I want to say that take something like this with the same oscillation, yeah? Then it will have bounded variation. It will be absolutely continuous if the corresponding series converges, you see? But derivative may be as large as we want, yeah? Clearly. Now look, now the lemma, since this is the same chapter, so lemma 8 now. The result that we used with you, not used, but I say that it can be used in order to see that Cantor staircase is not absolutely continuous. No, this is the next one. The previous one only that absolutely continuous function, if function is absolutely continuous on the interval AB, then it has bounded variation. Now let's see only this one. It has bounded variation on this interval AB. And then later we will see that if derivative is 0 almost everywhere, that function must be constant for absolutely continuous functions. Indeed, this is trivial, yeah, more or less, because we have finite interval. We have finite interval AB. Now, and this is absolutely continuous. Therefore, what can we do? We will divide, for any epsilon, we will divide this interval into huge, maybe, but finite number of small intervals, yes, such that the length of this interval, small interval, is smaller than given delta, yes? And then what we will have? We will have the total variation. It will be bounded from above by the epsilon, which is given beforehand, and the number of these steps, but number is finite. So for fixed epsilon, we will have very concrete number. So we can take any epsilon, for example, epsilon equal 1, proof for epsilon equal 1, from definition of absolutely continuous function, one can take delta corresponding to definition of absolutely continuous function, yeah? From definition of absolutely continuous function. Then what do we have? Then we can take m capital natural number such that m capital is larger than b minus a divided by delta, by this delta. Very big maybe, but concrete finite number. It's easy to see. It's easy to see that the variation of function on the interval is less or equal than m. Less or equal than m. Why? Why do we have this? Because look, we take any partition. What does it mean, bounded variation? We take any partition of this interval AB, yes? Now, and we consider the, what do we consider? We consider the f of xk plus 1 minus f of xk, yes? We consider this one, k from 0 to n minus 1, okay? We want to show that this is less or equal than some finite number. Why this is smaller than n? Because we can collect together all points which belongs to this interval, yeah? And then for all these points, it will be, so it will be decomposed. It will be decomposed as one sum, second sum, and the last sum, which corresponds to this decomposition. And this sum is smaller than 1, this sum is smaller than 1, this sum is smaller than 1. And the number of these sums, it is just m, okay? So it will be just smaller than m. Is it clear or not? Please. Once more. On this interval, maybe there are many points. But for all of them, by the definition of absolute continuity, the corresponding difference will be smaller than 1, since the sum of them, the sum of these differences, the sum of this length of interval is smaller than delta. Okay? No objections to that fact. Okay, no objections. Now I have no time to prove with you next lemma. In next lemma we will see with you that important property of absolutely continuous functions is that they have the property, this property is in calculus. We remember that in calculus, if function is differentiable, then we have that it is the zero, yeah, if derivative. But of course, the fact from calculus is valid till now. If derivative is zero everywhere, then of course function is constant, yeah? But now, if derivative is zero almost everywhere, then it's not necessary function is constant. Please look at counterfunction. But if, in addition, the function is absolutely continuous, then yes. And this is very close to the one useful characterization that I'm going to give you next time in 1 week, Banach-Zaretsky theorem. This characterization of absolutely continuous functions, that function is absolutely continuous if and only if, look, function is absolutely continuous if and only if it has bounded variation, it is continuous, so just inside of this intersection, we understand it's not enough, and plus it has some additional so-called Lusin property. The Lusin property says that function maps the set of zero measure onto set of zero measure, okay? Pre-image has zero measure, then image has zero measure. Lusin property, sometimes it's called, okay? So counter function doesn't have this property. The measure of counter set is zero, but image, it has measure 1. So, okay? So there is this theorem. I will give you theorem next time without proof. And this is characterization that says that some subclass from here is absolutely continuous. So, when will you bring me homework?
When do you want?
No, this week at least. Okay? Okay. Okay, that's all. Huh?